Good day, everyone. Our topic for today is about linear Diophantine equations. In this video, we discuss equations in two variables called Diophantine equations. These kinds of equations require integer solutions. It means the solution to our linear Diophantine equations should be all integers. Now, the goal is to present the set of points that determine the solution to this kind of equations. In geometrical sense, the Diophantine equation represents the equation of a straight line. That is, if we graph the Diophantine equation, the graph is a straight line. Here, we need to find the points whose coordinates are integers and through which the straight line passes. Now, here's the definition of a linear Diophantine equation, or you may read this as linear Diophantine equation. So it is a linear equation of the form ax plus by equals c, where a, b, and c are all integers. So note again here that a solution to the linear Diophantine equation, say we have x sub 0, y sub 0, it requires x sub 0 and y sub 0 to be all integers. Follow? We also note here that the Diophantine equation may have integer solution, or it is also possible to have no integer solution. Now, this theorem describes the case in which the Diophantine equation has a solution, and it also shows what are the solutions of such equations. Now here, the equation ax plus by equals c has integer solutions if and only if d divides c, where d is the GCD of a and b. If the equation has a solution, say x equals x sub 0 and y equals y sub 0, then we can say that there are infinitely many solutions, and the solutions are given by x equals x sub 0 plus the product of b over d and t. And for y, it is equal to y sub 0 minus the product of a over d and t, where t is an arbitrary integer. Now let me elaborate what this theorem all about. Because we have here if and only if. It means two implications. That is, we have the necessary and sufficient conditions. So for the first, we have if ax plus by equals c, this is our linear Diophantine equation. If this has an integer solution, then we can say that d, which is the GCD of a and b, divides c. Then the other way, if d divides c, where d is the GCD of a and b, then we can say that our linear Diophantine equation ax plus by equals c has integer solutions. Now take note here, if our linear Diophantine equation has integer solutions, say we have one solution, x sub 0, y sub 0. That is, x is equal to x sub 0 and y is equal to y sub 0. Now, if our linear Diophantine equation has one solution, then we can say that our linear Diophantine equation has infinite solutions. We have here the ordered pair or the coordinate x and y, where x is equal to x sub 0
plus we have here the product of b over d and t. And then for our y, we have this form, where t again is an arbitrary integer. So please do not forget this one because we will be using this one later on. Now, what about if our linear Diophantine equation has no solution? Or when can we say that our linear Diophantine equation has no integer solution? So to answer that one, we can also restate the theorem such that it describes the case in which the Diophantine equation has no solution. So in that case, we will be using this statement here. So this statement, we have here, if our linear Diophantine equation ax plus by equals c has integer solutions, then we can say that d divides c, where d is the GCD of a and b. Now, if we're going to get the contrapositive of this statement, we will arrive at this. So the contrapositive is, if d does not divide c, where d is the GCD of a and b, then our linear Diophantine equation ax plus by equals c has no integer solution. So that's what we are going to look into later on, in which, given the our linear Diophantine equation ax plus by equals c, we will be looking into if d divides c or d does not divide c. Follow? So if d divides c, we can say that our linear Diophantine equation has an integer solution, as what this theorem is saying. So if d divides c, our linear Diophantine equation has an integer solution. However, if d does not divide c, we can say that our linear Diophantine equation has no integer solution. Hello? Now let's have here an example. So to elaborate this concept. Now, for example, we have the linear Diophantine equation 2x plus 4y equals 9. Here, a here is 2. We have a is equal to 2, this one. And then b here is 4. And then we have here c, which is equal to 9. Okay, note here that our GCD, the GCD of a and b, this is equal to, our a is 2, our b is 4, the GCD is 2. And this is our d. Now we will be looking whether, we will be finding rather whether d divides c. So for this condition, d divides c or d does not divide c. So again, recall that if d divides c, where d is the GCD of a and b, this means our linear Diophantine equation with this equation has integer solutions. However, if d does not divide c, this means our linear Diophantine equation has no integer solution. Hello? So, as simple as that. So here, d is 2, and then c is 9. It means 2 does not divide 9. Hello? Here, d does not divide c. 2 does not divide 9. Why? Because we cannot write 9 as the product of 2 and an integer k. Hence, because 2 does not divide 9, we can say that 2x, our linear Diophantine equation, 2x plus 4y equals 9 has no integer solution. So as simple as that. So you just follow this one. This one. You just check if D divides C, then we can say that our linear Diophantine equation has integer solutions. However, if D does not divide C, therefore we can say that the linear Diophantine equation has no integer solution, as what this example is telling us. Now let's have another example. What if we have this linear Diophantine equation? 2x plus 4y is equal to 8. Now here, A is equal to 2, B is equal to 4. We have A, B, and then C is equal to 8. So we will be looking into our GCD of A and B, or our D. So we have here the GCD of A and B is 2. Follow? It is 2. And this is our D. So again, we will be testing if D divides C. Here, does D divide C? So in this case, D is 2. And then our C is 8. Now in this case, 2 divides 8. Why? Because we can write 8 as the product of 2 and an integer. So that is 8 can be written as 2 times an integer 4. That's why we can say that 2 divides 8. Now in this case, from our previous theorem, we can say that our linear Diophantine equation, 2x plus 4y equals 8, has integer solution. Okay, in fact, there are infinitely many integer solutions. Why? Now let's try to recall this theorem here that if, by the way here, if they divide C, we can say that our linear Diophantine equation has integer solutions. Now, if it has solution, say we have here x sub 0 and x sub 0, rather y sub 0, the coordinates x sub 0, y sub 0, we have this one. We can say that the linear Diophantine equation has infinite solutions. We have here the coordinates x, y, where x is in this form and then y is in this form, where t here is an arbitrary integer. Here, we will get, in our example here, we will get a particular solution. By the way, this is a particular solution here, this one here is our particular solution. Then our infinite solution can be written in this form. As you can see here, it is based on our particular solution. No, x sub 0, y sub 0. So here we will be using the trial and error method. Take note that we have our linear Diophantine equation. So we are to first find a particular solution. So for our particular solution, we have x sub 0, coordinates x sub 0 and y sub 0. We will be using here the trial and error method. So we will use this Diophantine equation. So we have x sub 0 plus 4y sub 0 equals 8. So we will be using this one. And then we will try to find, by using the trial and error method, we are going to find x sub 0 and y sub 0. So we have here 2 times what number plus 4 times what number is equal to 8. So we will be using here trial and error method. Please take note here that we can have any solution to this one. So our the first thing that we're going to get is a particular solution, just one solution. So here we can have x sub 0 be equal to 2, and then y sub 0 be equal to 1. As you can see here, 2 times 2 is 4, plus 4 is 8. Hence here, our x sub 0 is equal to 2, and y sub 0 is equal to 1 by using the trial and error method. Now, in that case, we can now write our infinite solution in this form. So we can write our infinite solutions. The coordinates x and y, where x rather is equal to, we have here x sub 0. Our x sub 0 is equals 2. So this is 2 plus we have b over d. So take note here, b is 4 over d. D here is 2 times t. Hence, x here is equal to 2 plus, by the way, this is 2. 4 over 2 is 2 times t. So for our y is equal to y sub 0. Now here we have our particular solution where y sub 0 is equal to 1. So we have here 1 minus, we have a over d. So a is 2 and d is 2 times t. Hence, y is in the form 1 minus t. So we have here our infinite solutions in this form. Okay, it's 1. So that will be our answer. That would be our answer. Now, let's try to check our answer, our infinite solution, if it satisfies our linear Diophantine equation. So to check, take note here that t is any integer, an arbitrary integer. So we can let, say for example, t is equal to 1. So let's try to have, so for this one, x is equal to, using this one. So we have 2 plus 2 times 1 because t is 1. Therefore, x is equal to 4, 2 plus 2. And then y here, this form, 1 minus t. So we have 1 minus 1 is equal to 0. Now, using this one, our solution, let's try to check if the values here will satisfy our linear Diophantine equation, which is 2x plus 4y equals 8. So we have here 2 times, our x here is 4, plus 4 times our y is 0. So is this equal to 8? So here, this is 8 plus 0 is equal to 8. Hello? Now let's try another value of t. So t is equal, say for example, t is negative 1. This means we have x is equal to 2 plus 2 times negative 1 here. So this is equal to 2 plus negative 2 is 0. Then for y, we have here y equals 1 minus t. So our t is negative 1. So we have 1 minus negative 1 is the same as 1 plus 1. This is 2. So using these values here, we will try to check if it satisfies the Diophantine equation. So 2 times plus 4 times, okay. So we have 2 times our x is 0. Here our y is 2. So this is 0 plus 4 times 2 is 8 equals 8. So any values of integer t here will satisfy our linear Diophantine equation because we know that our solutions are correct. Hello? Note here that our infinite solutions will base on the particular solution that we choose. Now let's choose another particular solution. So here,
we have chosen here for our particular solution, x sub 0 equals 2 and y sub 0 equals 1. Now notice that in these linear Diophantine equations, there are infinitely many integer solutions to this one. Hence, we can have different solution in this case for our particular solution. We can have different values for x sub 0 and y sub 0. Now, what will happen to our infinite solutions? So we have written that in this form. Hence, if we have different particular solution, we have chosen different particular solution, so this will be changed. Hello? So let's choose another particular solution. So let's have here, let's have for our particular solution using again our linear Diophantine equation, 2x plus 4y equals 8. So this is our linear Diophantine equation. Now let's have choose a particular solution for our ordered pair x sub 0, y sub 0. So again, let's have this one plus 4. Okay, we will be using trial and error method. So we can choose, we can have 6 here. So 2 times 6 is 12. Plus, we may have negative 1 here because we know that 12 plus, this is negative 4 is equal to 8. Now in this case, x sub 0, this is x sub 0 is equal to 6 and y sub 0 is equal to this one, negative 1. So we have this as our particular solution. So what will happen to our infinite solution in that case? So take note here for our infinite solution. Okay, infinite solution, ordered pair xy. X can be written as this one. We have x sub 0 plus the product of b over d times t. So here now, our x sub 0 is 6. So this now becomes 6 plus b over d. So recall that our b is 2 and then 4 rather. Our b here is 4. This is A, B, C. And then our d is 2. So b over d is 4 over 2 times t. So this is equal to, x is equal to 6 plus 2t. So this will be our x for our infinite solution. And then y is equal to, we have y sub 0 is negative 1. Here, negative 1 minus a over d. So a here is 2 over 2t. Hence, y can be written as negative 1 minus t. So here, this is our infinite solution based on our particular solution that we have chosen. The particular solution we have 6 and negative 1. Now to check our answer, let's try to check. So we let t be any integer. Say, let's have t is equal to 1. So x is equal to this one. Let's refer this from here. So 6 plus 2 times 1 is equal to, this is 8. Now our y is equal to negative 1. This is our y. So negative 1 minus 1, t is 1, is negative 2. Follow? Hence, from our linear Diophantine equation, 2x plus 4y equals 8, we have 2 times our x is 8 plus 4 times our y is negative 2. Is it equal to 8? Here, 2 times 8 is 16 minus, we have here 4 times 2 is 8. So 4 times negative 2 is negative 8. That's why we have here minus 8. So 16 minus 8, is it equal to 8? Of course, 8 is equal to 8. So again, here you can let any integer t to check your work.
As you observed here, for our linear Diophantine equation, 2x plus 4y equals 8, we have showed the infinite solutions in different representations or forms based on the particular solution we have used. To summarize, for our linear Diophantine equation, 2x plus 4y equals 8, for our particular solution, first, x sub 0 is equal to 2 and y sub 0 equals 1. And then we came up to our infinite solutions. X equals, in this form, x sub 0 plus b over d times t. We have this form. We have 2 plus 2t. And then y is 1 minus t. And then for our second solution, we have a particular solution, x sub 0 equals 6, y sub 0 equals negative 1. And we came up to our infinite solutions, x equals 6 plus 2t, and then y equals negative 1 minus t. Now, as you observe here, we have showed the infinite solutions in different representations or forms. We based it on the particular solution that we have used. So as you can see here, we have 2, 1. So we have here 2, 1. And then here we have 6, negative 1. So we have here 6, negative 1. But this same, we have 2t. We have here minus t. Okay? Therefore, if the linear Diophantine equation has a solution, then you can write its infinite solutions in different forms based on the particular solution you use. Follow? So that's all about linear Diophantine equations. Now, I hope this video lecture helps you a lot in understanding the concept of the linear Diophantine equation. I hope you know already how to determine when is the linear Diophantine equation has or has no integer solution. Also, how to find the infinite solutions. Lastly, I hope this video lessens your confusion in finding the infinite solutions of the given linear Diophantine equation. So before I end this video, let me say this one. Please take note that if the linear Diophantine equation has integer solutions, then the infinite solutions would be based on the particular solution you have used. So thank you for watching. God bless everyone and keep safe always.